For this course, you also need to consider cubic and quartic graphs. So I'm going to introduce you to them now as an extension on the quadratic graphs. Just to remind you, a quadratic graph could either be a positive parabola or a negative parabola. These are the quadratic graphs. There's two options there, depending on if A is positive or negative. Okay, so that's what they look like. If you were to go one step backwards, you have linear graphs, which are straight lines. And a quadratic graph would have an equation y equals ax squared plus bx plus c, which is, we looked at that in the previous video. And linear graphs would have equation y equals mx plus c, where m is the gradient and c is the y-intercept. And you should have covered that a lot on your GCSE course, but that will be covered a bit later on in this course as well. So kind of a step up from that, you have linear, then quadratics. The next one is called a cubic, and then the one after that is called a quartic. You could keep going, so order 5 would be a quintic, hexic, septic, octic, nontic, dectic, and so on. But we only study up to quartic on this course. Okay, so the shapes of the cubics. Well, for the quadratics, when A was positive, we had a positive U shape. And when A was negative, we had a negative N shape. But for cubics, there are 3 different shapes that you could get for each sign of A. So there's 6 altogether. So we've actually increased the number of different shapes that we can get. And when you study calculus, particularly differentiation, you'll study these in a lot more detail. And also consider the cases using what we call the Factor Theorem, which again is something else that we learn on this course. So with the quadratic case, you had one turning point. You always had exactly one turning point. No more, no less. Exactly one. Now a turning point is a point where the curve turns around. So this point here is called a turning point because it was going down and now it's going up. So this point here is called a turning point. It's also all turning points have a zero gradient. Now, a gradient is, again, something you'll study when we do differentiation in a lot more detail. But for now, we're going to say that the gradient is the gradient of the tangent. Okay, so the gradient of the curve is the gradient of the tangent. That's what we'll say for now. So we can see the gradient here is horizontal, so it's got a gradient of 0. The same here. And if the gradient is 0, then it's called a stationary point. So these are stationary points. And we can see that this cubic has precisely 2 stationary points, one which we call a maximum and one which we call a minimum. And both of these stationary points are turning points. So this is a minimum, which is a type of turning point, and this is a maximum, which is also a type of turning point. Now, all turning points are stationary points, but not all stationary points are turning points, because we can have a point on a curve which has a 0 gradient, which is not a turning point. So, for example, this one here, it has a 0 gradient at this point, but it's not a turning point because it was increasing at this point before it, and it's still increasing afterwards. So it hasn't turned the curve around like the max or the min has, but it's kind of got stationary, and then it started to increase the gradient again. And this is another type of stationary point, but it's not a turning point. It's important to distinguish between the two. And we call this one a stationary point of inflection. And again, inflection points will be studied in a lot more detail when you study calculus. And then this one here, this cubic, doesn't have any stationary points, and that is very possible. So a cubic could have 2 stationary points, 1 stationary point, or no stationary points. Whereas the quadratic always had exactly 1 stationary point. So that's the main difference between them. If A is negative, then these kind of get mirrored. So we could have another curve with 2 stationary points, but this time the minimum occurs first, and then we have the maximum. We could have a negative gradient going into a stationary point of inflection, and then negative gradient to follow, or the whole thing has a negative gradient. Okay, and again, these correspond to your turning points, your stationary points. So 2 on that one, or you could have 1 on this one, or none. All right, so those are the cubic shapes. Quartic shapes then, these get even more complicated again. These are ones that you need to be familiar with for the course. So I've drawn 6 curves for the quartics, and these are all where A is greater than 0. So all the positive quartics. If you want to get the negative quartics as well, then you need to mirror image them vertically. So imagine they're reflected in the x-axis. So y equals ax to the 4 plus bx cubed plus cx squared plus dx plus e, where a, b, c, d and e are any constants. Positive, real, or no, not positive, just real constants. And if a is positive, then we end up with one of these 6 shapes. So for a quartic curve, you could have a curve which has 3 stationary points. And in general, if you have an nth order polynomial, then you can have up to n minus 1 stationary points. And they'll all be turning points if that's the case. Okay, so that's our, there's 3 turning points there. This one here has got 1 turning point, which is a little local minimum. And then we also have a stationary point of inflection kicking around over here. Okay, the gradient is 0 at this point, but it's not a min or a max. So it's a stationary point, but it's not a turning point. This one here is exactly the same, but it's been mirror imaged in the y direction, if you like, the y-axis. And then we have the minimum coming second. Or we could have a situation like this one, where there's just 1 turning point. That's the only stationary point on the curve. It looks like a parabola, it looks like a quadratic. It's not. It doesn't have the same properties that a parabola would have. And it's much steeper, gets much steeper much quicker. Or you could have one which is not symmetrical. So with a parabola, they are always symmetrical, but quartics, they are not necessarily symmetrical, because you could have this little wobble out to one of the sides before it kind of shoots off to your infinity direction. So with a parabola, your turning point was halfway between any 2 points on the where a horizontal line will cross the curve. It's not the case for a quartic. As you can see on this one, it's closer to this side than it is to that side. If I were to draw this horizontal line in there, right, you can see that the turning point is much closer to this one than it is to this one. It wouldn't happen with a parabola or a quadratic curve. Okay, so those are the main shapes. I'm not going to go into much detail past that for now. I have got a little summary table which I would like to introduce to you. So properties of the cubic and the quartic. So the cubic equation, y equals ax cubed plus bx squared plus cx plus d. The number of roots it can have is either 1, 2 or 3. Okay, if we consider drawing a horizontal line for the x-axis, it has to cross the x-axis at least once on all of these curves, but it could cross it twice. So for example, if I continued this gradient across, then it would cross the x-axis at this point and touch the x-axis at this point, or it could cross it 3 times in situations like that, but it has to cross it at least once. So that's what I mean by number of roots. If a is greater than 0, then the cubic will start low and end high. Okay, starts low and ends high, low, high, low, high, low, high. If a is negative, it will start high and end low. Start high and low. High, low, high, low. The number of turning points it can have is either 0 or 2. Okay, no turning points on these 2 or 2 turning points. But the number of stationary points, again, important to distinguish between a turning point and a stationary point. It could have 1 stationary point, which is this point here. Okay, it's not a turning point, but it is a stationary point. Same stats then, but for the quartic. The equation is y equals ax to the 4 plus bx cubed plus cx squared plus dx plus e. It can have either 0, 1, 2, 3 or 4 roots. Now it can have 0 roots, whereas the cubic couldn't. The quartic can. Okay, let's go to the quartic curves. If I were to draw my x-axis down here, we can clearly see that this curve would never cross the x-axis. And in fact, any even polynomial, that is the highest power of the polynomial, is an even number, it doesn't have to have any roots. So if it's odd, it has to have at least one. It could have one root, so if this curve here were sitting on the x-axis, then that would have one root. It could have two roots, so if that were the x-axis, it would cross it twice. It could have three roots. In fact, none of my graphs would offer a three-root solution, but let me do a quick sketch of one down here. You can get ones that look like that. It doesn't have to be symmetrical like this one is. This one here would offer three roots. So if I could draw the x-axis along here, then we can see there'll be a root there, a root there, and a root there. So it's three roots. Or it could have four roots. If we were to cross the x-axis across anywhere along there, it would cross the curve 4 times, having 4 roots. If a is greater than 0, it starts high and ends high. If it's less than 0, it starts low and ends low. The number of turning points, it's either 1 or 3. Okay, the quartic curve must turn around because it starts high and ends high, which means it must have an odd number of turning points, or it starts low and ends low. And the number of stationary points, well, it could have 2 stationary points if one of those stationary points was, for example, here, a stationary point of inflection. Okay, so that's the very general theory for these types of graphs. As I said, you will study these in a lot more detail when you study calculus and the factor theorem. Okay, thanks for watching.